Yep, so I'm going to talk about percolation on finite transitive graphs. I'll say right now that it's joint with Tom Hutchcroft. And basically, we've proved a reasonably old conjecture about percolation on finite transitive graphs. What I plan to do is give you a bit of the background, first on general percolation theory and then on the specific problem. And there are one or two parts of the proof that are rather additive combinatorial in nature. So there's quite heavy use of approximate groups, for example. I'm going to leave that fairly hidden, to be honest, but people who are familiar with that area will recognize where it comes in, I think. And then there's also a part of the argument where we use generalized arithmetic progressions in abelian groups. And I hope I'll have time at least to tell you a little bit about how that particularly additive combinatorial aspect of the proof comes in. But I'll start by just giving a bit of background to the problem. So basically, in percolation theory is about ultimately about a certain means of defining random subgraphs of a given graph. Okay, so if you start with a graph G with a vertex set V and edge set E, which classically will be some kind of lattice, like the square lattice that I've drawn here. This is just one part of the infinite square lattice. You start with this given graph G, and then for a given P between 0 and 1, we define a random subgraph, which I'll call G sub P, which has the same vertex set as the original graph and some random subset of the edges, which I'll call EP for now. And we define this by basically each edge we look at independently, and we decide at random whether or not to include it in this set EP, and the probability of including an edge is just P. Okay, so by taking each edge in E independently at random in EP with probability of inclusion equal to P. Okay, so basically you're looking at each edge of this graph independently at random, and you're either retaining it or deleting it, and P is the probability that you retain the edge. So you end up with a random subgraph of the original graph. Something like this, perhaps. Okay, so you have some edges included, some edges not included. And the sort of first classical question that's asked about this random subgraph is, what is the probability that GP has an infinite connected component? And I think defining a random subgraph like this is probably quite natural to combinatorial audiences. There are some serious physical motivations for asking this question. The original motivation, I think, was to look at the flow of water through a porous stone. There's also a famous application to studying the behavior of magnets at high temperatures. So there are some serious kind of physical questions underlying this question. But I think as a combinatorial object, it's also, I think, quite natural. And this, I hope, comes across as a fairly natural question. So we'll call this probability psi sub G of P. And And so, yeah, so there's this question, what is this probability? I'm going to tell you a couple of basic facts about it. So the first fact is that regardless of the graph G and regardless of the probability P, this probability is either 0 or 1. Okay, so psi sub G of P, the probability that the random subgraph contains an infinite connected component is always equal to 0 or 1. I won't write this down, but that it's basically a consequence of Kolmogorov's 0-1 law. The key point is that whether the random subgraph has an infinite connected component or not doesn't depend on any finite set of edges. So if that's familiar to you, then hopefully that's explained it. If not, I think it's probably best if I just ask you to take my word for it. There's some kind of standard probability theory that explains this. And then another fact which seems obvious, it's not quite as obvious as it seems, but it's equally it's not hard. It's that there exists a value PC of G between 0 and 1, such that this probability of having an infinite component is 0 if P is below PC and is 1 if it's above PC. Okay, so if you set P equal to 0, then you're just deterministically deleting all the edges. Of course, you don't have an infinite connected component. And as P increases, to start with, you have no infinite connected components, and then you reach this critical value PC. And then all of a sudden, the behavior jumps. And for all P larger than PC, you do have an infinite connected component with probability 1. Okay, and this PC is called the critical probability. Okay. So we know that, or I've told you that this probability of having an infinite connected component is either 0 or 1. And I've told you that there's some critical value at which it flips from being 0 to being 1. And so this classical question, what is this probability of an infinite connected component? We now have a slightly more precise version of it, which is what is the value of PC for a given graph G? So I've swept something under the carpet a little bit there, which is that I haven't said anything about what happens when P is equal to PC. And in general, that depends on the graph, and there are lots of graphs for which it's not known. And I think there are some quite interesting open problems still in that direction, but that's not going to be at all the focus of this talk. So I don't really want to say any more about that. But still, there's this question, what is the value of PC for a given graph G? And actually that question also turns out to be quite hard in general. There are some graphs, I think probably the most famous graph which is known is this infinite square lattice. So it's known that PC of z squared is equal to a half. That's, well, one direction is due to Harris in 1960. I think he proved that PC was at least a half. And then Keston proved the harder direction, PC is at most a half, in 1980. And the fact that there was a 20-year gap between these two directions, I think already gives you some idea of how difficult computing these critical probabilities can be. But indeed, in general, it's hard. So there's a slightly easier question, which is also now a standard type of question that people ask about these models, which is, so easier question. When is PC, or when is PC strictly between 0 and 1? Okay, so when, and this is when this happens, we have what's called a non-trivial phase transition. So you really have non-trivial values of P for which you don't have infinite components, and you have non-trivial values of P for which you do have infinite components. Okay, so this is a general question that is often asked about percolation on graphs. Okay. Now, it turns out that, so basically every graph we look at in this talk is going to have bounded degree. And it turns out that if G has bounded degree, then PC is always at least 1 over the degree minus 1. That's a standard fact in percolation theory, at least that should be. So basically, if we're dealing with bounded degree graphs, then we sort of get this PC being bounded away from 0 for free. So the remaining question is, for which graphs do we have PC strictly less than 1? Okay, so that's the question that I'm going to focus on in this talk. When is PC strictly bounded away from 1? When do we have a non-trivial phase transition from no infinite connected component to having infinite connected components? Okay. Now, classically, lots of graphs that were looked at in the context of percolation are basically lattice type graphs. So for example, this square lattice, or you have triangular lattices and higher dimensional variants. But a natural generalization of all those types of graphs is called transitive graphs. So we're going to be interested in transitive graphs. And basically a graph is transitive. So G is transitive if for all vertices X and Y, there exists an automorphism such that, well, that takes X to Y. Okay, so basically a graph is transitive if you can't tell the difference between any of the vertices. Okay, so in particular, the square or high dimensional hypercubic lattices are all transitive, but this is a much broader class than that. And in 1996, Benjamini and Schramm, I should write the year, 1996, conjectured a very precise criterion that should decide whether or not a transitive graph has PC less than 1. They conjectured the following. Suppose G is an infinite transitive graph, then PC of G strictly less than 1 if and only if, I'm going to write something in inverted commas for now, and then I'm going to explain a bit more precisely what I mean. If somehow G is not one-dimensional. Okay, and I'm going to make that condition very precise in just a second, but this is the kind of broad idea. So this is partly motivated by this special case of Z to the D, the hypercubic lattice. So PC of Z to the D is strictly less than 1 if and only if D is bigger than 1. And it's very clear what we mean by dimension in the case of Z to the D. And their conjecture is essentially a generalization of this criterion to arbitrary transitive graphs. So how do we understand dimension? Basically, we understand dimension in terms of the volume growth of G. Okay, so that may mean something to some people, not everyone. I'm going to tell you exactly what I mean by it, so don't worry. So I'm first of all going to write beta sub G of R to be the number of vertices in a ball of radius R with respect to the graph metric on G. So since we're assuming G is transitive, this doesn't depend on the center of the ball. So this is a well-defined quantity. So for example, let's just do a quick picture of in Z squared. So if we look at a ball with this as its center, the ball of radius 1 is just the set of all points that are neighbors of the center. The ball of radius 2 is a set of all points you can get to from the center by crossing at most 2 edges, and so on and so forth. Ball of radius 3 looks like that. Okay. And a standard fact about transitive graphs, or locally finite transitive graph, about transitive graphs, is that if G is transitive and infinite, let's say, just for ease of notation, then either the size of these balls grows faster than any polynomial, in which case we'll say that G is infinite dimensional, or the balls grow exactly like some polynomial of integer degree. I'll write down exactly what I mean by that. Or there exists an integer d, natural number d, and constants big C and little c, bigger than 0, such that the ball of radius r is at least little c r to the d, and the size at most big C r to the d for r. Okay, so either the balls of G grow faster than any polynomial, or they grow exactly like some polynomial of integer degree, where exactly like a polynomial means this up to constant multiples. Okay, and in that case, we'll call D the dimension of G. Okay, so I'm using dimension in a slightly loose fashion, but hopefully it's clear enough for the purposes of this talk.
So is this a deep fact? Does this like depend on Gromov's theorem or something?
Yes, it does depend on Gromov's theorem, and for transitive graphs, it depends. There's another result of Trofimov, which shows that if you have a transitive graph of polynomial growth, then it's quasi-isometric to a Cayley graph, and then you apply Gromov's theorem to that Cayley graph and get the same conclusion. So it also depends on the Bast-Gibbard formula, which computes the growth of nilpotent groups. But yeah, it does depend on Gromov's theorem. Thanks for the question. And yes, I'm about to mention those theorems actually, as it happens. So so results. So theorems of Gromov and Trofimov, both from the 80s, imply that if the dimension of G is finite in the sense I've just described, so if there's a polynomial, if there's some polynomial upper bound on the size of balls in G, then I don't want to make this very precise for the purposes of this talk, but then G is approximated in some very precise sense by a Cayley graph of a nilpotent group. Okay, so one can make much more precise what exactly I mean by this is approximately equal to. For the purpose of this talk, I just want to say that it's equal to in a sense that preserves the probability of the property of PC being less than 1. So from the point of view of the question we're treating here, whether or not PC is less than 1 or not, this approximation is good enough that we can basically assume that G is a Kelly graph of a nilpotent group in the finite dimensional case. All right. So again, this is another point where if I had more time, I would go into a bit more detail. For people who are familiar with Gromov's and Trofimov's theorems, this will perhaps be already what I just said will be obvious. If not, I'll ask you to take my word for it. But I do want to tell you one, if you're not familiar with these theorems, there's one consequence of this is that if the dimension of G equals 1, then basically G looks like a kind of fastened line. Okay, so it's a sort of thickened line. And the reason I mentioned that is because in this Benjamini-Schramm conjecture, G being one-dimensional was exactly the condition that is conjectured to be equivalent to having PC equal to 1. So what Benjamini-Schramm's conjecture says, from a more geometric point of view, is that PC is strictly less than 1, if and only if G is not a thickened line. Okay. It's another way of interpreting their statement. Now I say Benjamini-Schramm's conjecture. In fact, this is now a theorem. Let me say that this is now a theorem due to several authors. Dumino Copin, Goswami, Ralphie, Severo, and Yadin. Very recently, published in 2020. It was on the archive in 2018, but published in 2020. So they very recently verified this conjecture of Benjamini-Schramm that PC less than 1 for infinite transitive graph corresponds exactly to the dimension being bigger than 1, or to the growth rate being superlinear. All right. Now, I said that these percolation problems are in some sense motivated by physical questions like the flow of water through a stone or the behavior of a magnet at high temperatures. In that spirit, I think it's quite natural to wonder what happens in finite graphs as well as infinite graphs. Benjamini, back in 2001, made a very precise conjecture, which is an analogue of this Benjamini-Schramm conjecture for finite transitive graphs. Okay, and that is what I want to focus on for the rest of the talk. Now, of course, in a finite transitive graph, you can't define PC in the same way. Of course, the random subgraph you get of a finite graph is not going to have an infinite connected component, so you have to make things a bit more quantitative. And so if G is finite, we'll define PC of G rather than to be the probability at which G, the random subgraph starts having infinite components. We'll define it to be the probability at which the random subgraph starts having components that contain a positive proportion of the vertices. So I'll put inf of such that probability GP contains a component with at least, say, half the vertices of G. And let's say we want that probability to be at least a half. Okay, so in the infinite setting, it's the edge retention probability at which you start seeing infinite connected components. In the finite setting, it's the edge retention probability at which you start seeing large components with high probability, where large I've arbitrarily defined to be half the number of vertices and high probability I've defined to be at least half. Of course, you could replace either of these halves with any other parameter between 0 and 1, and it would still make sense. And in fact, it turns out that by some standard percolation techniques, the question I'm about to ask is essentially equivalent for all values you put here. So I don't want to go into detail about that, but you can reduce. If I put 0.99 in both of these places, there's a straightforward reduction that reduces that question to the questions I've written. So these halves, not only are they arbitrary from the point of view of making the question make sense, they're completely arbitrary from the point of view of answering it as well. Okay, so I hope that's clear. What I mean, not why it's true. It shouldn't be clear why it's true. But, okay, so we define this. I think it's a fairly natural way for defining PC. There are some competing definitions of PC, but this is somehow the strongest one. This is the one where we can answer the question. So I'll stick with this one. Right. So Benjamini conjectured in 2001 basically a very similar condition to what we see in the infinite setting. If G is finite, transitive, and I'm going to say degree of G, meaning the number of neighbors, the number of edges containing any one point, is bounded by K. Then there exists epsilon, depending only on K, positive, such that PC of G, such that if G is not one-dimensional, again in a sense that I will make precise in just a second, then PC of G is almost 1 minus epsilon. So the presence of this epsilon was not really necessary in the infinite setting, but in the finite setting, for this to be meaningful, we do need to have some kind of uniform bound on how far PC is from 1. Because of course, once you fix a given graph, if you make P enormous, but not quite equal to 1, then you can make it so that with high probability all the edges are included or something. So for any given graph, of course, this PC is strictly less than 1. For it to be meaningful, you need to have some quantitative bound, uniform bound over all graphs. And in his conjecture, this bound is allowed to depend on the degree of G. And again, that's what we prove. Okay. So that's a sort of slogan version of the conjecture, this not one-dimensional. It turns out that in the case of a finite graph, making precise what we mean by not one-dimensional is a little bit more subtle than in the case of an infinite graph. Let me just give you a quick illustration of why that is. So if we just first of all look at Zn, so I'm going to write Zn, I'm going to use that to abbreviate the integers mod n. So that basically looks like a cycle. And I hope we can all agree that it would be natural to think of this as being one-dimensional. On the other hand, if you have Zn squared, hypercubic torus, then again, I hope we would all agree that I hope there would be no strong disagreements if I claimed that I wanted to view that as being two-dimensional. But there's a sort of in-between case in the finite setting that doesn't really happen in the infinite setting. And that's if you have something like Zn plus Zm with m much bigger than 1, but n much bigger than m. So you have a very, very, very long, thin torus, like n by root n or something. It's not altogether clear for what values of m, if m is 1, then this is one-dimensional. If m is n, this is two-dimensional. But for m in between, it's not completely clear at what point this long, thin torus moves from being one-dimensional to being two-dimensional. Okay, so that's one of the subtleties that arises in this finite setting. But in any case, Benjamini does give a very precise criterion for what the interpretation of one-dimensional should be for this problem. And in fact, the precise hypothesis in the conjecture is that the diameter of G, so that's just the maximum distance between any 2 points, any 2 vertices of G, should be at most the number of vertices divided by log of the number of vertices. Okay, so I don't want you to worry too much about exactly what that means. What I would like to do is illustrate which of these examples are covered by this criterion and which are not covered by it. And then I want to give you another sort of geometric interpretation of what graphs are not covered by this. And that I hope will give you a good intuitive idea of the scope of this conjecture. So basically, if you have an n by log n torus, then that is covered. So Benjamini conjectures, or it's actually what has been known for some time actually that this is true. I think that's one of the motivations for the conjecture. But an n by log n torus, his conjecture says you should have PC bounded away from 1. But if instead of log n you have something smaller, say root log n, then his conjecture will no longer apply. And indeed, it's an exercise to check in that case that PC is not uniformly bounded away from 1 as n goes to infinity. Okay. And then just as in the infinite case, I told you that any graph that's one-dimensional in the growth rate sense that I described, anything not covered by this is basically a thickened cycle. Okay, thickened by at most log of the length of the cycle. Okay, so essentially what Benjamini conjectures is that if you have a finite transitive graph that doesn't look like this, then its PC is bounded away from 1. Okay. And Tom and I, actually, before I tell you what we've done, I should tell you what other people have done. So this was a conjecture in 2001, and there was some progress not too long afterwards. So this conjecture is known for expanders, which in particular have logarithmic diameter, so they certainly satisfy this condition. And that was due to Alon, Benjamini, and Stacy in 2004, I think. It's also known for abelian groups, or abelian Cayley graphs, I should say. But not all abelian Cayley graphs, just if you take what I would call the standard generating set with respect to standard generating sets. So basically, in this case, you would take the generator and that generator. Okay, so you just take you maybe I should write it down. You write using the fundamental theorem of finite abelian groups. You know that this is the form, this form, and you just take all these as your generators. So if you have this very specific Cayley graph of an abelian group, then this conjecture is known, and that is due to Malone and Pack in 2006. Okay, so it's known for expander graphs, and it's known for some very specific abelian Cayley graphs. And as far as I know, it's nothing else is really known, or was really known. So theorem joint with Tom Hutchcroft, which well, I'll put 2021. That's when we put it on archive. It's still under review, not published yet, but we finished it last year, and we almost proved Benjamini's conjecture. We proved it under a slightly stronger diameter condition. So we prove that the conjecture holds if we assume that the diameter of G is at most the size of the number of vertices over log of the number of vertices to some power A. Okay, so the conjecture, in the conjecture, this A should be 1, and so we prove it up to logarithmic factors. And here A is an absolute constant. So it doesn't depend on the degree or the graph or anything. This is a completely absolute constant. To be honest, we haven't tried very carefully to compute what our argument gives for A, but I think we were convinced that certainly 500 or something like that is enough. And I'm sure if we were very careful, we could get it much lower. In some special cases, we know it. So, well, let me tell you one more thing actually before I say that. So we also show if G is an abelian Cayley graph, okay, with no restrictions on the generating set, then we may take A equals 1. Okay, so we do prove the full Benjamini's full conjecture in the case of an abelian Cayley graph, which is already a significant generalization of the Malone-Pack result. And we prove the full conjecture under this annoyingly slightly stronger hypothesis. Okay, and in I guess the 15 minutes I have remaining, I just want to tell you a little bit about the proof. Kevin's got a question there. Is there any guess as to how it depends on K? Yeah, good question. We haven't. So first, the first thing I should say is that so the question is, how does this epsilon in the how does epsilon depend on K? How does the bound depend on the degree? We basically don't know. We use the bounded degree assumption in quite a few different places. So I think whatever our argument tells you can probably be improved by being a bit careful in one or two of those places. So there's a corresponding question, which is in the infinite setting, rather than just proving that PC is bounded, PC is less than 1 for an arbitrary Cayley graph that has superlinear growth. Is there some? Can we bound PC away from 1 for an infinite transitive graph? And that was recently shown. It's recently shown that you can do that. So my work with Tom actually already gives a bound. A bound. Let me write it down. So we can show that PC is less than 1 minus delta, depending on the degree. So I'm using a different letter here because it's a different setting. So for an infinite graph, we can bound PC away from 1, depending only on the degree. And very recently, Panayotis and Severo removes the dependence on the degree from this bound. So they now have a uniform bound away from 1 for all Cayley graphs of superlinear growth, irrespective of the degree of the graph. Okay, so our bound here is for transitive graphs. Theirs is only for Cayley graphs, but still significant strengthening. And one of the key things they do is they basically take given a Cayley graph, they define what's called a minimal Cayley graph, which is a Cayley graph where if you removed any of the generators, then it would no longer be a generating set. And somehow, by looking at that, they're able to deal with a case where you have sort of lots of redundancy in the generators, which makes K very large and kind of ruins this bound. And I wouldn't be completely surprised if something similar were possible in the finite case, but we haven't thought about it. So whether epsilon really has to depend on K in the finite case is unclear. But our proof, I haven't looked through it carefully enough to be able to tell you how it depends on K as things stand. Does that answer your question, Kevin? Okay. Right. So I have about 10 minutes left. So let's see what we can do. First of all, I want to give you a very rough overview of, first of all, the infinite proof, which is this Dumont-Coppin and others. Basically, they prove if the dimension is strictly bigger than 4, or if the polynomial growth rate has degree bigger than 4, if you'd rather I phrase it like that, they can just prove directly that PC is less than 1. And in fact, the argument they use there has content for graphs that are not transitive as well. But I don't want to go into detail about that. If the dimension is at most 4, then so if the graph has polynomial growth of degree at most 4, then Gromov and Trofimov, as I mentioned earlier, imply that G is basically a nilpotent Cayley graph. Okay, and then it is known that up to changing the generating set, which in the infinite setting you can do without changing whether PC is more or less than 1, is less than 1 or not. So up to changing the generators, which once you know you're in the setting of a nilpotent Cayley graph doesn't matter for this question. You can assume that G has a subgraph that's isomorphic to the square lattice. Okay, so let me just, I don't want to go into detail about how you get that in general, but let me just give you one very specific example of a nilpotent group and show you where the z-squared lattice can be found. It's the famous example of the Heisenberg group, upper triangular 3x3 lattices, 3x3 matrices with 1s on the diagonal integer entries. That has a subgroup where this top entry is 0, and that subgroup is isomorphic to z-squared. So if you just pick the right generators of this to lie in your generating set of G, then you get a z-squared subgraph. Okay, and then once you know that your graph is a z-squared subgraph, the fact that PC of z-squared is less than 1 for free gives you that PC of the big graph is less than 1, because of course if this z-squared subgraph has an infinite connected component, when you add in all the extra edges from the rest of the graph, that certainly has an infinite connected component. Okay, so that is a rough outline of how their proof works. And by the way, let me emphasize that this top bit here, which I've completely glossed over, is by far the hardest bit of their proof. So I don't want you to misinterpret this this here as suggesting that their argument is anyway easy. There's some serious stuff going on in this bit. but that is, I think, a topic for a different talk. Now I want to show you how, or describe a little bit about how we adopt a similar approach in a finite setting, but also describe some of the problems. So firstly, if the dimension is bigger than, we need to take 11 rather than 4. If I had more time, I would go into a bit of detail about why, but basically for large dimensional graphs, we can adapt their direct argument and get something similar. Okay. If the dimension is at most 11, okay, so we can't really apply Gromov's theorem and Trofimov's theorem anymore because they only make sense for infinite graphs, but there's a famous, I suspect particularly within this audience, result of Brouillard, Green et al. Result using approximate groups that is that in particular gives a finitary version of Gromov's theorem. And then there's a similar finitary version of Trofimov's theorem due to Tessera and me. And basically, if you combine these finitary versions of Gromov and Trofimov in a similar way to what we do over here, we can, again, assume in the low dimensional case that G is basically a nilpotent Cayley graph. Now, already this is hiding a slight difficulty with the finite case compared to the infinite case, because whereas in the infinite case, there's this clear dichotomy between graphs that grow at a faster than polynomial of degree 4, or at most polynomial of degree 4. There's a real true dichotomy between graphs of dimension 4 and dimension bigger than 4. In the finite setting, things are a bit more subtle. So it's a bit related to the whether the dimension of a graph is equal to 1 that I told you about earlier. But again, let's imagine we have Zm to the 11 plus Zn with 1 much less than m much less than n. Okay, so this just with the standard generators, say. So if you look at balls up to radius roughly m in this graph, then this looks like a 12-dimensional graph. But once you get to radius m and start growing faster than that, you stop growing in one direction. Sorry, I got this the wrong way around. It should be that to the 11. You stop growing in this one direction, and now you're growing only in 11 dimensions. And so somehow at small scales, this graph looks like it's 12-dimensional, and at large scales, it looks more like it's 11-dimensional. And so there's somehow this crossover scale between the large dimensional and the small dimensional settings. And it turns out to be quite a delicate matter to separate the two different scales of the graph in this case. Okay, so I'm not going to have time to go into detail about that now, but there is this this is probably one of the most technically challenging parts of the proof is to resolve this absence of dichotomy that was so useful in the proof in the infinite case. Okay, right. I don't think I have time. I was going to say a little bit about the nilpotent setting. If there's time at the end, I might come back to it. But basically, this is also a bit harder. We can no longer just look at a subgraph like we did in the infinite case. Okay. If somebody wants to ask a question about it at the end, I can explain. But otherwise, I'll just tell you that we have to use induction to reduce to the abelian case. Okay, I'm going to also put that in red because that's a lot more involved than the corresponding step in the infinite setting. And then finally, of course, in the infinite setting, once we reduce to the z² case, we're done by a classical theory of percolation on z². But then again, here it's a little bit more difficult because, as I said earlier, even in the case of abelian Cayley graphs, Benjamini's conjecture was not known in general. So even once we reduce the abelian case, this still leaves us the difficulty of proving conjecture for abelian Cayley graphs. Okay, so that's another step which is significantly more involved in the finite case than the infinite case. Okay, so I have 3 minutes, which I will use to just give you a little hint about what's involved in proving this conjecture for abelian Cayley graphs. So basically, I told you that Malon and Pack proved this conjecture for abelian Cayley graphs with the standard generators. Actually, their argument gives something slightly stronger. It gives it for grids or boxes in Z to the D. Okay, so in abelian Cayley graph with the standard generating set, we'd be identifying the top and we'd be identifying the top and bottom and sides of this to make it into a torus, but they actually don't need that. They just need a grid. So they prove the conjecture or version for boxes in Z to the D. And so basically our approach is to reduce the setting of an arbitrary abelian Cayley graph to the Malon-Pack setting by finding a large subgraph of our abelian group, which is isomorphic to such a box. And if you think about it for a second, that amounts to finding a large, proper, generalized arithmetic progression inside G. Okay, so what we do is we prove the following result. Suppose G is a finite abelian group generated by x1 up to xr. Then there exists a proper generalized arithmetic progression P on these generators. I should use K, not R. I've been using R for the radius. Inside G with each Li at most the diameter of G, such that size of P is at least some positive proportion of the number, we're in a group of the number of elements of G. Okay, so we have to, given us a set of generators from an abelian group, we have to find a large, proper, generalized arithmetic progression on those generators whose diameter is not larger than the diameter of G. Okay, so I was hoping to say a little bit more about that, but I'm out of time, so I think I'll have to stop. But basically, once you have this JP, you have a box like this that's dense inside your group, and then you can apply the Malon-Pack result to that. Okay, I think I need to stop there. Thanks very much.